we shall do a general formalism of the currents in magnetostatics. The current in a wire is the charge per unit time passing through a given point. By definition, negative charges moving to the left count the same as the positive ones to the right. And it is measured in coulomb per second or amperes, where 1 ampere is equal to 1 coulomb per second. In the preceding sections, we shall try to understand the different configurations of currents. The first one is the current due to a line charge. Let us consider a wire through which there is a flow of charges. We denote lambda as the charge per unit length, that is dq over dl. If we assume a very small length dl of the wire, then this can be written as the velocity of the charges multiplied by the time it takes to traverse that length, that is v times delta t. We can show that the current through such a configuration is a vector quantity. We have I is dq over dt, and this is equal to dq over dt multiplied by dl over dl, and that is equal to dq over dl, then dl over dt. We have defined lambda to be the charge per unit length, that is dq over dl. Therefore, this equation is lambda multiplied by v. So, this is the magnitude. Vectorially, it is I equal to lambda times vector v. We will now try to formulate an expression for the magnetic force on a current carrying conductor. For that, we will consider the same wire element and we will place that in an external magnetic field B. Now, the magnetic force F mag, this is equal to integral V cross B dq. This is equal to integral V cross B dq can be written in terms of the line charge density lambda as lambda times dl, and this is equal to integral lambda V cross B dl, and this is nothing but I cross B dl. Therefore, the equation for the magnetic force on a current carrying conductor, which is subject to an external magnetic field P, is I cross B integral I cross B dl. There is one more variation for this equation. We'll see how. So F mag, as we have seen, is equal to integral I cross B dl. We'll write the current I as I dl hat. Since direction of I is along the direction in which the unit vector dl hat is oriented. Therefore, this is I dl hat cross B dl, and this is equal to I times dl hat cross B, and this is equal to integral I dl cross B. Typically, the current is constant in magnitude along the wire, and in that case I comes out of the integral. Therefore, we have F mag equal to I integral dl cross B. Moving to the second configuration of current, and this is known as surface current. A surface current flows on a very thin surface, as you see in this figure. The thickness of the surface is infinitesimally small. When a charge flows over the surface, we describe it by the surface current density K running parallel to the flow. So you can see the flow is towards the right, and we define a new entity known as the surface current density K that is running parallel to the flow. For that, what we do is that we will choose a ribbon of infinitesimal width dl perpendicular. What you see in black on the surface is a ribbon of infinitesimal width dl perpendicular. If the current in this ribbon is di, the surface current density is defined to be K equal to di over dl perpendicular. In other words, K is a current per unit width. We denote this width as dl perpendicular because this width is perpendicular to the direction of current flow. In particular, if the surface charge density is sigma, where sigma is defined to be dq over dA, and the velocity of the charges is v, then we can write the surface current density as K equal to sigma times v, where v is the velocity. Let's check dimensionally whether this is correct. K is given by Coulomb per meter square is the dimension for sigma, multiplied by meter per second. Meter square and meter gets cancelled, and then we have Coulomb per second over meter, and that is ampere per meter. In general, K will vary from point to point over the surface, reflecting variations in sigma and or v. We shall now formulate the magnetic force on a surface current. The magnetic force is F mag. This is equal to integral V cross B dq, and this is equal to integral V cross B dq will write as sigma times dA. This is equal to integral sigma V cross B dA. Therefore, the magnetic force due to a surface current is integral K cross B dA. The third current configuration is volume current. To define the volume current, we will consider the flow of charge as distributed throughout a three-dimensional region. So what you see in this figure is a pipe through which some charges are flowing. To understand the volume current density, we will consider a tube which is lying inside the volume parallel to the direction of the flow. We will also consider a very small cross section dA perpendicular, which is perpendicular to the direction of flow. If the current in this tube is di, we define the volume current density as J equal to di over dA perpendicular, and the unit is ampere per meter square. That is, J is the current per unit area. If the mobile charge density is rho, that is, rho is defined to be dq over d tau, and if the velocity is v, then we can write the volume current density J as equal to rho v. Let's check whether it is dimensionally correct. We have J as Coulomb per meter cube multiplied by meter per second. Meter and meters cube will get cancelled. So this is Coulomb per second per meter square, and that is equal to ampere per meter square. We shall now try to find out the expression for the magnetic force on the surface current. We have F mag. This is equal to integral V cross B dq. This is again equal to integral V cross B, then rho d2, that is equal to integral rho V cross B d2, and thus the magnetic force due to a volume current density is integral J cross B d2. So this is a summary of what we have learned. The general expression for the magnetic force is F mag equal to integral V cross B dq. The magnetic force on a line current is F mag equal to integral I cross B dl, and the magnetic force on a surface current is F mag equal to integral K cross B dA, and the magnetic force on a volume current is F mag equal to integral J cross B d2. We shall now try to understand what are meant by steady currents. Stationary charges produce electric fields that are constant in time, hence we have the term electrostatics. Whereas steady currents produce magnetic fields that are constant in time, and the theory of steady currents is known as magnetostatics. Formally, we define the electrostatics as dou rho over dou t equal to 0, and we define the magnetostatics as dou J over dou t equal to 0.